Hello and welcome back. I'm so glad you're here. Tonight we're doing something a little different. We're not focusing on what science has figured out, but rather on what it hasn't. The mysteries that remain, the questions without answers, the places where our understanding simply stops. So get comfortable. Adjust your pillow. Let your body sink a little deeper into the mattress. Before we begin, I'd love to know where you're watching from tonight. And how was your day? Drop a comment below. I always enjoy reading your comments. If you enjoy falling asleep to this kind of content, consider subscribing. It helps the channel reach others who are searching for the same thing you found. Now let's begin. We'll start with something so fundamental. It almost sounds impossible. More than 95% of the universe is made of substances we've never directly detected or understood. Scientists call them dark matter and dark energy, though these names are really just placeholders, labels for our ignorance dressed up in scientific language. Think about that for a moment. Everything you've ever seen, touched, or experienced, every star in the night sky, every planet, every galaxy, every atom in your body, all of it combined makes up less than 5% of what exists. The rest is invisible, undetectable, known only through its effects, like footprints in snow left by someone you can't see. It's humbling, in a way. We've mapped the human genome, landed rovers on Mars, peered back to nearly the beginning of time itself, and yet the universe is mostly made of something we can't even describe. Perhaps that's why they call it dark. Not because it's sinister, but because we're fumbling in darkness, trying to understand what it could possibly be. Dark matter doesn't emit light. It doesn't absorb light. It doesn't reflect light. By all accounts, it should be completely invisible. And yet, we know it's there. We know because when we look at galaxies spinning, they rotate in ways that shouldn't be possible based on the visible matter alone. Stars on the outer edges move too fast. They should be flung out into space like water droplets spinning off a wheel, but they're not. Something invisible is holding them in place. It's a bit like watching an invisible person dance. You can't see them, but you can see their footprints appearing in the snow, one after another, tracing the steps of something real but imperceptible. That's dark matter. We see its gravitational fingerprints everywhere, pulling on galaxies, bending light, shaping the large-scale structure of the cosmos itself. And yet, no detector on Earth has ever captured a dark matter particle. We've built elaborate experiments deep underground, shielded from cosmic rays, waiting for the faintest whisper of a dark matter collision. So far, silence. Whatever it is, it passes through us, through the Earth, through everything, like we're not even here. Then there's dark energy, which is somehow even stranger, where dark matter at least behaves like matter, pulling things together with gravity. Dark energy does the opposite. It pushes. It's causing the universe to expand, not just steadily, but faster and faster, accelerating outward like a car with the gas pedal pressed down and no one behind the wheel. Scientists discovered this by accident in 1998. They were studying distant supernovae, expecting to find that the universe's expansion was slowing down over time, the way a ball thrown upward eventually slows before falling back. Instead, they found the opposite. The expansion was speeding up. It was as if the ball, instead of slowing, was flying upward faster and faster, defying everything they thought they understood about gravity. No one knows what dark energy is. Some think it might be a property of space itself, that empty space has energy, and as the universe expands and creates more space, there's more energy, which pushes things apart even faster. Others think it might be a new kind of field permeating everything. Or perhaps our understanding of gravity breaks down on cosmic scales, and what we're calling dark energy is really just evidence that Einstein's equations need correction. Whatever it is, it makes up about 70% of the universe, and we have no idea what it's doing or why. Here's another mystery that cuts right to the heart of existence. There's more matter than antimatter in the universe, and there shouldn't be. According to our best theories, the Big Bang should have created equal amounts of both. Matter and antimatter are like perfect opposites. When they meet, they annihilate each other in a flash of pure energy, leaving nothing behind. And yet, here we are. Here everything is. Stars, planets, galaxies, you, me, all made of matter. If the universe had been perfectly balanced, matter and antimatter would have destroyed each other completely, leaving nothing but light expanding into emptiness forever. No atoms, no chemistry, no life, just energy, cooling and fading into the void. But somehow, somewhere in the first moments after the Big Bang, there was an imbalance. For every billion particles of antimatter, there were 1,000,000,001 particles of matter. That tiny excess, 1 part in a billion, is everything that exists today. The extra particles that didn't have an antimatter partner to annihilate with were the cosmic leftovers. Why? No one knows. Scientists call this mystery baryogenesis, and they've proposed various mechanisms that might create such an imbalance, but none have been confirmed. It's one of those questions that sounds abstract until you realize. This is why anything exists at all. And then there's perhaps the most intimate mystery of all, consciousness. You're experiencing it right now, the feeling of being you, of thoughts arising, of awareness itself. But science can't explain it. Not really. We can map brain activity. We can see which neurons fire when you see the color red, or feel pain, or remember a childhood moment. We can correlate mental states with physical states down to remarkable precision. But none of that explains the subjective experience, what philosophers call qualia, the redness of red, the painfulness of pain, the you-ness of you. Neuroscientists call this the hard problem of consciousness. The easy problems, relatively speaking, are things like how the brain processes information, stores memories, or controls movement. Those can be studied with electrodes and scanners and experiments. But the hard problem is something else entirely. How does physical matter, neurons, chemicals, electrical signals, create the inner felt experience of being alive? Some think consciousness might emerge from complexity, the way wetness emerges from water molecules. Others believe it might be fundamental to the universe itself, like mass or charge. And some think we might never solve it, that consciousness might be the one thing that can't fully understand itself, a mirror that can't reflect its own reflection. Time itself is a mystery, though we experience it constantly, moment by moment. It flows forward, always forward, carrying us from past toward future, like a river that never reverses course. You can't unbreak a dropped cup, can't unsay a spoken word, can't return to yesterday. Time's arrow points one direction only, and yet when physicists look at the fundamental laws of nature, the equations describing how particles move, how forces interact, how energy transforms, they find something strange. Almost all of these laws work equally well forward or backward in time. If you filmed most physical processes and played the video in reverse, you'd see something that looks perfectly allowable by physics. A ball rolling up a ramp looks as valid as a ball rolling down. So why does time only go one way for us? Why do we remember the past but not the future? Why do cups break but never spontaneously reassemble? The answer seems to be related to entropy, the tendency of systems to move from order to disorder. A broken cup is more disordered than an intact one, and the universe seems to favor increasing disorder. But this just pushes the mystery back. Why did the universe start in a state of such low entropy that there was room for entropy to increase? Why was the beginning so orderly? No one knows. Time flows forward, and we flow with it. From birth toward sleep, from past toward whatever comes next, following an arrow whose origin remains mysterious. Let's drift now into the quantum realm, where mysteries multiply like reflections in facing mirrors. Here's one of the strangest. Quantum particles can exist in multiple states at once, a phenomenon called superposition. An electron can be in two places simultaneously. A photon can take multiple paths at the same time. A particle can be spinning both clockwise and counterclockwise until something observes it. It's not that we don't know which state the particle is in. It's that the particle itself hasn't decided yet. It exists in a ghostly combination of all possibilities. A kind of quantum, maybe. Neither here nor there, but somehow both and neither. Imagine flipping a coin and having it land as both heads and tails at the same time, remaining in that impossible state until someone looks at it. Then, and only then, does it choose. That's superposition, though even that metaphor doesn't quite capture the strangeness, because the coin doesn't secretly have a definite state we just can't see. It genuinely exists in an undecided limbo until measurement forces a choice. Physicists use superposition constantly. It's why quantum computers can explore many solutions simultaneously. It's confirmed by countless experiments, and yet it defies every intuition we have about how reality should work. Maybe that's the lesson. Reality at its deepest level doesn't care about our intuitions. It does what it does, strange or not. But superposition leads to an even deeper mystery, the measurement problem. When does a quantum system stop being in superposition and collapse into one definite state? And what counts as a measurement? These sound like technical questions, but they cut to the heart of what reality is. The mathematics of quantum mechanics is astonishingly accurate, the most precisely confirmed theory in all of science. It can predict probabilities perfectly, telling us exactly what percentage of the time we'll measure each possible outcome. But it can't tell us when or why the probabilities become actual outcomes. It can't explain what happens during measurement to make the quantum coin finally choose heads or tails. Some interpretations say consciousness is required, that the act of a conscious observer looking at something causes the collapse. Others say it happens automatically when quantum systems interact with large, classical objects. Still others deny that collapse happens at all, proposing instead that every measurement creates parallel universes where each outcome occurs. We can calculate what will probably happen, but we can't explain what probably means or when probably becomes actually. The math works perfectly. The meaning remains obscure. Perhaps that's enough. Perhaps the universe is content with probabilities, with maybes, with questions that linger. And then there's entanglement, what Einstein called spooky action at a distance, and he meant it as a criticism. He thought it was so absurd that it proved quantum mechanics must be incomplete. But experiments proved him wrong, and now we're left with the spookiness. When two particles become entangled, they remain connected across any distance. Measure one, and you instantly know something about the other, even if it's on the opposite side of the universe. Change one, and the other changes correspondingly, faster than light could travel between them. Not because information is traveling, no signal passes between them, but because they're part of a single quantum system, a unified thing that transcends space. It's as if you separated a pair of magic dice, carrying one to Tokyo and leaving the other in New York. When you roll your die in Tokyo and get a 6, the die in New York, rolled at the same moment, also shows 6, not sometimes, but every single time, correlated in ways that seem impossible. Einstein thought this meant quantum mechanics was missing something, some hidden variables that determine the outcome in advance. But experiments testing Bell's inequality have shown that no such hidden variables exist. The connection is real, instantaneous, and fundamentally mysterious. The universe, at its deepest level, is not made of separate things, but of relationships, connections that persist across the void. Here's a question that seems almost absurd in its simplicity. Why does the universe have 3 dimensions of space and 1 of time? Why not 2 spatial dimensions, or 4, or 10? Why not multiple dimensions of time? It seems like an arbitrary choice, and yet it defines the entire structure of reality as we experience it. In 3 spatial dimensions, gravity follows an inverse square law. Double the distance, and gravitational force becomes 1/4 as strong. This turns out to be crucial for stable orbits. In 4 spatial dimensions, orbits would be unstable. Planets would either spiral into their stars or drift away. In 2 dimensions, complexity seems impossible. There's not enough room for the intricate networks that life requires. Some physicists working on string theory propose that the universe actually has many more dimensions, 10 or 11 in total, but that the extra dimensions are curled up so small we can't perceive them. Others think different dimensions might exist in parallel, separate from our own, but no one knows why the universe selected this particular arrangement. Why 3 and 1 rather than some other combination? Maybe it's the only stable configuration. Maybe there are other universes with different dimensions, and we simply exist in one where observers like us can arise. Or maybe there's a deeper principle we haven't discovered yet, some reason written into the fabric of reality that makes 3 + 1 the only genuine option. For now, it remains another mystery, the shape of the stage on which everything plays out, taken for granted, because we've never known anything else. The universe, it turns out, appears to be fine-tuned for life in ways that border on the miraculous, or at least the statistically improbable. The physical constants that govern reality, the strength of gravity, the charge of an electron, the mass of a proton, the speed of light, all seem calibrated to exquisitely precise values. Change any of them by even a tiny fraction, and the universe becomes inhospitable to life as we know it. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. Slightly weaker, and, Stars might never ignite at all. If the strong nuclear force were a bit different, atomic nuclei couldn't form. No carbon, no oxygen, no chemistry. If the electromagnetic force varied, atoms couldn't bond into molecules. The list goes on, constant after constant, each sitting in a narrow range that allows complexity to exist. It's like discovering that someone rolled 100 dice and got sixes on every single one. Possible, yes, but so improbable that you'd suspect the dice were loaded, that something more than chance is at work. Some scientists propose a multiverse, countless universes with different constants, and we simply find ourselves in one of the rare ones where observers can exist. It's the anthropic principle. We're here because we couldn't be anywhere else. Other universes might exist where gravity is too strong or electrons are too light, but no one's there to notice because no one could be. Others see it as evidence of design, though that raises questions science can't address. And some think there might be a deeper theory, not yet discovered, that explains why these constants must have the values they do. That what looks like fine-tuning is actually necessity disguised as coincidence. For now, though, it remains a mystery. We live in a universe that seems calibrated for our existence, and we don't know why. And that leads directly to another question, perhaps even more fundamental. Why do these constants have the specific values they do? Not just why they're in life-permitting ranges, but why these exact numbers? Why is the speed of light 299 sub 792 of 458 meters per second and not some other value? Why does the electron have the precise mass it does? Physics can measure these constants with extraordinary precision. We know their values to many decimal places, but knowing the number and understanding why it's that number are entirely different things. It's the difference between reading a thermometer and understanding why water freezes at 0 degrees Celsius. Some constants seem to be related to each other through mathematical relationships, suggesting they might not all be independent. But we don't have a theory that derives their values from first principles. We can't calculate what the speed of light should be. We have to measure it and plug it into our equations. Perhaps a final theory, a theory of everything, would show that these constants couldn't be any other way, that they emerge necessarily from deeper mathematical truths. Or perhaps they're genuinely arbitrary cosmic accidents frozen into the fabric of reality during the Big Bang. We might be asking for an explanation where none exists, searching for meaning in numbers that are simply given, like asking why circles have to do with the number pi. They just do. Reality is what it is. Here's a mystery that physicists find particularly vexing. Gravity is absurdly, incomprehensibly weaker than the other fundamental forces. It's called the hierarchy problem, and it's not subtle. Gravity isn't just a little weaker. It's weaker by a factor of about 10 to the 36. That's 10 followed by 36 zeros. A 1 with 36 zeros after it. To put that in perspective, a small refrigerator magnet can pick up a paperclip, overcoming the gravitational pull of the entire Earth. The electromagnetic force in that tiny magnet defeats the gravity of a planet with 6 trillion kilograms of mass. That's how weak gravity is. Why? No one knows. The other forces, electromagnetism, the strong nuclear force, the weak nuclear force, are all roughly comparable in strength, but gravity is an outlier, so weak it barely registers, except when you accumulate enormous amounts of mass. Some theories propose that gravity might be leaking into extra dimensions, spreading its influence across spaces we can't perceive, which would make it seem weaker in our three-dimensional world. Others think it might be a clue that we don't understand gravity properly, that it's fundamentally different from the other forces in ways we haven't grasped yet. Or perhaps it's just another arbitrary feature of the universe, like the constants we discussed before, something that simply is, without deeper justification. But it troubles physicists because it seems like such an enormous coincidence, like finding one ant in a colony of trillions that's somehow different from all the others for no apparent reason. Let's drift back now to the beginning of everything, to the Big Bang itself. We can trace the universe's history back to incredible closeness, to the start, to the first second, the first microsecond, even the first nanosecond after everything began. But there's a boundary we can't cross, a moment so early and so extreme that our physics simply breaks down. We don't know what happened in the very first fraction of a second, a period called the Planck epoch, lasting only about 10 to the negative 43 seconds. That's a decimal point followed by 42 zeros and then a 1, an unimaginably brief instant. In that moment, the universe was so hot, so dense, so energetic, that quantum effects and gravitational effects were equally important. And that's a problem, because we don't have a theory that successfully combines quantum mechanics with gravity. When we try to calculate what should happen under those conditions, our equations produce infinities and nonsense. So we're left with a fundamental gap in our understanding. We can't see the universe's birth moment. It's like a story missing its first page, or a video that starts a fraction of a second after the crucial event. Everything after that first moment we understand reasonably well. The universe cooled, particles formed, forces separated, matter condensed. But that initial instant remains shrouded, perhaps forever, in mathematical impossibility. Some think a theory of quantum gravity, string theory, loop quantum gravity, or something else, will eventually let us peer into that earliest moment. Others suspect that asking what happened then is like asking what's north of the North Pole, a question that seems meaningful but actually isn't. Time itself might have emerged from the Big Bang, making before a meaningless concept. We often talk about the Big Bang as an explosion, but that's not quite right. It wasn't an explosion in space, it was an explosion of space. Space itself expanded, carrying everything with it, and it happened everywhere at once. Imagine a balloon covered with dots. As you inflate the balloon, the dots move apart from each other, but none of them is the center of expansion. From any dot's perspective, all the others are moving away. That's the Big Bang. Not an explosion from a point, but an expansion of the fabric itself. And that leads to a strange conclusion. If you ask where the Big Bang happened, the answer is here, and also there, and everywhere. Because every point in space was present at the beginning, compressed together into an infinitely dense state. The spot where you're lying right now, in some sense, was also present at the Big Bang, along with the location of every distant galaxy. It's not that everything flew apart from some central location. It's that all locations were once the same location. It's enough to make your mind fold in on itself a bit, which is fine, because we're drifting here, not cramming for an exam. The universe's origin resists easy visualization because it involves the origin of space itself, and we're beings who exist in space, using spatial metaphors to think. We're trying to imagine something that lies outside our frame of reference, like a character in a painting trying to understand the canvas. And then there's the question of what came before, which might not have an answer. If time itself began with the Big Bang, then before is meaningless, like asking what's colder than absolute zero or what color precedes red in the spectrum. Some theories propose a cyclical universe or a multiverse or quantum fluctuations giving rise to space-time, but these push the mystery back rather than solving it. The origin of everything remains stubbornly mysterious, perhaps appropriately so. Now let's jump forward to the present universe and one of its more recent mysteries, fast radio bursts. These are intense pulses of radio waves from deep space, lasting only milliseconds, but releasing as much energy as the sun does in several days. They were first detected in 2007, and for years, astronomers weren't even sure they were real. The problem was that they were so brief and unpredictable that by the time anyone noticed one in the data, it was long over. It was like hearing a strange sound in the night. Was it real, or did you imagine it? Early fast radio bursts were found only in archived data, never in real time, which made them scientifically frustrating. Eventually, though, more were detected, and patterns began to emerge. Most come from distant galaxies billions of light years away. Some repeat at irregular intervals, others have been observed only once. The leading theory now is that many are caused by magnetars, neutron stars with incredibly powerful magnetic fields. But this doesn't explain all of them, and the exact mechanism remains unclear. What makes them so energetic? Why do some repeat while others don't? Are they all caused by the same phenomenon, or are we lumping together different events that just happen to look similar? The universe is sending us these millisecond postcards from across cosmic distances, and we're still trying to decipher the message. It's worth noting that when fast radio bursts were first discovered, there was briefly excitement about whether they could be artificial, signals from alien civilizations. That possibility is now considered extremely unlikely, given their properties and distribution, but it's a reminder of how little we understand about the universe's more exotic phenomena. Mysteries abound, even in the forms of energy that reach us. Speaking of cosmic mysteries, let's turn to something called the cosmic microwave background, the afterglow of the Big Bang, a faint radiation that fills all of space, a whisper from the universe's infancy. Astronomers have mapped this radiation with exquisite precision, and it's remarkably uniform across the sky. The same temperature in every direction to within 1 part in 100,000. But there are anomalies, cold spots that shouldn't exist according to our models, unexpected patterns. One particular cold spot is so large and so unexpected that when it was first confirmed, some scientists half-seriously wondered if it could be evidence of another universe bumping into ours. That sounds like science fiction, but it's based on real observations. The cold spot is about 1.8 billion light years across, an enormous region where the cosmic microwave background is cooler than average. Some think it might be a supervoid, a vast region with less matter than usual, which would gravitationally affect the light passing through it. But even accounting for that, the cold spot seems too cold, too large. Other explanations have been proposed. Maybe it's a statistical fluke, one of those things that happens by chance if you look at enough data. Maybe our models of the early universe need adjustment. Or maybe, and this is the most speculative, it's a bruise left by another universe colliding with ours before inflation carried it away forever. Probably it's something mundane that we'll eventually understand. But for now, there's a cold patch in the sky, a departure from perfection, and we don't fully know why. The universe's baby picture has a strange shadow in one corner, and we're still trying to figure out what caused it. Inflation theory is widely accepted among cosmologists, but it's worth sitting with the strangeness of what it proposes. For a brief moment, a tiny fraction of a second, the universe expanded faster than light, doubling in size again and again in intervals so brief that trillions could fit in a blink. This doesn't violate relativity because space itself was expanding. Nothing was moving through space faster than light, but it's still extraordinary. A region smaller than an atom inflated to larger than our entire observable universe today, in less time than it takes light to cross a single proton. And then, just as suddenly, it stopped. Inflation ended. The exponential expansion ceased, and the universe settled into the more leisurely expansion we observe today, where galaxies drift apart over billions of years rather than microseconds. Why? What triggered the end of inflation? Energy from the inflaton field supposedly converted into matter and radiation, heating the universe and beginning what we think of as the normal Big Bang. But the details remain murky. We don't know what the inflaton field is made of, what potential energy landscape it was sliding down, or what made it reach the bottom and convert into particles. Some versions of inflation suggest it never truly ended, that different regions of space stopped inflating at different times, creating a multiverse of bubble universes, each with potentially different properties. Our universe would be just one bubble among countless others, still expanding in an eternally inflating megaverse. It's speculative, perhaps untestable, and yet it emerges naturally from the mathematics of inflation. Sometimes solving one mystery opens a door to infinite others, like a set of Russian dolls that never stops. Here's another cosmic coincidence that troubles physicists. The universe appears to be spatially flat. Not flat like a piece of paper. It still has 3 dimensions, but flat in the sense that parallel lines stay parallel forever, that the angles of triangles add up to exactly 180 degrees, that the geometry follows the rules you learned in high school. This might not sound mysterious until you realize how improbable it is. The universe could have been curved, either positively like a sphere or negatively like a saddle. And if it started with even the tiniest curvature at the Big Bang, that curvature should have grown over time. A slightly closed universe should have collapsed long ago. A slightly open universe should have expanded so fast that galaxies never formed. But the universe is flat, or so close to flat that we can't measure any deviation. It's like balancing a pencil on its point, possible in principle, but requiring such precise initial conditions that you'd never expect to find it that way by accident. Inflation provides an explanation here too. If the universe expanded exponentially, any initial curvature would have been stretched out, flattened like the surface of a balloon inflated to enormous size. Stand on Earth and the ground looks flat because the curve is so gentle. Inflate the universe enough, and any curvature becomes similarly imperceptible. But again, this requires inflation to have happened, and requires it to have inflated the universe by just the right amount, enough to flatten it, but not so much that, well, actually, in most inflation models, the universe should be much, much flatter than we observe. The observable universe should be a tiny speck in an incomprehensibly larger inflated space, which might be true but raises questions about why we observe what we do. The flatness of space seems like another parameter fine-tuned to a suspicious degree. Another cosmic coincidence that either points to deeper principles we don't understand or reminds us that we exist in a universe that permits our existence, whatever the odds. Let's turn our attention now to magnetars, neutron stars with magnetic fields so powerful they border on the incomprehensible. A typical neutron star is already extreme, the crushed core of a massive star, packed so densely that a teaspoon of its matter would weigh as much as Mount Everest. But magnetars take it further. Their magnetic fields are a quadrillion times stronger than Earth's. A quadrillion, that's a million billion. If a magnetar existed halfway between here and the moon, its magnetic field would be strong enough to erase every credit card on Earth. It would disrupt the molecular bonds in your body, interfering with the chemistry that keeps you alive from hundreds of thousands of miles away. And we don't fully understand how they form. The leading theory is that they're born in especially energetic supernovae, where the collapsing core spins rapidly and somehow amplifies magnetic fields to these staggering strengths. But the details remain unclear. How does the field get so intense? Why do some neutron stars become magnetars while most don't? What determines the field strength? Magnetars occasionally have what astronomers call starquakes. The solid crust of the star cracks and shifts, releasing enormous bursts of X-rays and gamma rays. In 2004, a magnetar 50,000 light-years away had such an outburst. The wave of radiation reached Earth and measurably affected our planet's ionosphere. From 50,000 light-years away, a star the size of a city briefly outshone everything in the sky except the sun and moon. These objects exist at the edge of what matter can do, pushing physics to extremes we can barely study. They're laboratories of strong field physics, places where magnetic forces overwhelm even gravity, where the structure of space itself might be affected, and they remind us that the universe contains conditions so extreme they make anything on Earth seem gentle by comparison. Now let's drift closer to home, to a mystery that's haunted observers for centuries: ball lightning. People have reported seeing glowing spheres of light floating through the air during thunderstorms, drifting through rooms, bouncing off walls, sometimes passing through windows or closed doors as if they weren't there. The reports span cultures and centuries, described by enough credible witnesses that it's hard to dismiss as mere folklore, and yet science has struggled to explain it. Ball lightning is rare, unpredictable, and typically lasts only seconds. Very few photographs exist. Laboratory attempts to recreate it have produced ambiguous results, things that might be similar or might be entirely different phenomena. No consensus theory explains how it forms, what sustains it, or how it can behave the way witnesses describe. Some proposals involve plasma, ionized gas held together by electromagnetic forces. Others suggest it might be a silicon vapor created when lightning strikes soil, burning slowly in a ball. Still others invoke more exotic physics, miniature black holes, antimatter, or knots in electromagnetic fields. Each theory has problems, fails to explain certain observations, or requires conditions that seem implausible. It's humbling in a way. We've split the atom, mapped the human brain, detected gravitational waves from colliding black holes, and we still can't definitively explain a glowing ball that sometimes appears during thunderstorms. Nature keeps a few secrets close, even when they occur in our own atmosphere, visible to the naked eye. Perhaps that's part of the appeal of ball lightning. It's one of the last everyday mysteries, something your grandmother might have seen through her kitchen window, something that resists easy explanation despite our technological sophistication. A reminder that the world can still surprise us. In 1977, a radio telescope in Ohio detected something extraordinary. A powerful signal from space that lasted 72 seconds, rising and falling in intensity in a pattern that looked exactly like what you'd expect from a distant, focused transmission. The astronomer reviewing the data was so struck by it that he wrote, "Wow," in the margin of the computer printout. The signal has been known as the WOW signal ever since. It came from the direction of Sagittarius, from a region of sky with no nearby stars or obvious sources. It was at a frequency of 1420 megahertz, a special frequency in radio astronomy, the frequency at which hydrogen naturally emits radiation, and one that many scientists think might be used for interstellar communication because it's so fundamental. And then it was gone, never repeated. The telescope swept over that same patch of sky again and again in following days, weeks, years. Nothing. Other observatories have looked. Still nothing. It was as if someone turned on a powerful radio transmitter, aimed it at Earth for just over a minute, and then switched it off forever. Was it aliens? Probably not, though we can't rule it out. More likely, it was some natural phenomenon we don't fully understand. Perhaps something involving a neutron star, or interstellar hydrogen clouds, or even a glitch in the equipment, though that seems less likely given the signal's characteristics. Recent work has suggested it might have been caused by a passing comet, though this explanation is controversial. What haunts astronomers is the uncertainty. We have 1 minute and 12 seconds of data from nearly 50 years ago, and that's all we'll ever have unless it happens again. A cosmic mystery frozen in time, a printout with WOW scrawled across it, and no way to know for certain what we were listening to. The universe sent us a message, and we're still trying to decide if it meant anything at all. Let's return to something more fundamental: mass. Why do particles have mass? It's a question that sounds almost silly. Of course things have mass. You might think, that's just how matter is. But the deeper you look, the stranger it becomes. The Higgs boson, discovered in 2012, provides part of the answer. Particles acquire mass by interacting with the Higgs field that permeates all of space. The more strongly a particle interacts with this field, the more massive it is. Photons don't interact with it at all, which is why light is massless and can travel at the speed of light. Electrons interact weakly, so they have little mass. Top quarks interact strongly, so they're much heavier. It's a beautiful mechanism, confirmed by experiment, and it earned a Nobel Prize. But it doesn't answer everything. Why does the electron have the specific mass it does? Why is a top quark 350,000 times heavier? Why does the Higgs field have the strength it does? The Higgs mechanism explains how particles get mass from the field, but not why the field gives them the particular masses they have. Moreover, the Higgs mechanism only accounts for about 1% of your mass. The rest comes from the binding energy of quarks inside protons and neutrons, the energy of the strong force holding them together, converted to mass by Einstein's EMC2. But again, why those particular energies? Why those binding strengths? At the deepest level, mass emerges from fields and forces and interactions, from the quantum structure of reality itself. But why reality has the particular structure it does, why the parameters are set to these values rather than others, remains mysterious. Mass is something we experience every moment, gravity pulling us down, inertia resisting our motion, and yet its origin remains only partially understood, like knowing how a clock works, but not why time flows. Neutrinos are sometimes called ghost particles, and it's apt. They're produced in enormous numbers. Nuclear reactions in the sun create so many that trillions pass through your body every second, but they barely interact with matter. A neutrino could pass through a light year of lead and probably not hit anything. Most of them travel through Earth like it isn't there, through you, through everything, ghosts in the machine of reality. We can detect them, but only barely, using enormous detectors buried deep underground to shield from cosmic rays. You might capture a few neutrinos per day out of the trillions passing through. It's like trying to have a conversation during a hurricane. Most of the signal is lost in noise and distance. But here's where it gets strange. Neutrinos oscillate. They come in 3 types, or flavors: electron neutrinos, muon neutrinos, and tau neutrinos. And as they travel, they shift between these types. A muon neutrino produced in the sun might arrive at Earth as an electron neutrino. They don't stay what they are. They change, flickering between identities like quantum chameleons. This oscillation proves that neutrinos must have mass. Massless particles can't oscillate this way. But the standard model of particle physics originally predicted they should be massless. Their mass is also incredibly small, at least 1,000,000 times less than an electron, which is already the lightest massive particle we knew about. Why are they so light? Why do they oscillate? We can describe the phenomenon mathematically, but understanding why it happens, what determines the mixing angles and mass differences, remains unclear. And there's another mystery. Are neutrinos their own antiparticles? Most particles have distinct antiparticles, matter and antimatter, but neutrinos might be Majorana particles, identical to their own antiparticles. Experiments are searching for a rare type of radioactive decay that would prove this, but so far, the answer eludes us. These ghost particles keep secrets even as they pass through us. Dark energy is accelerating the universe's expansion, pushing galaxies apart faster and faster. We've covered that, but what happens next? Will this acceleration continue forever, or might it change? And if it continues, where does the universe end up? Nobody knows for certain. The most straightforward prediction, given current observations, is that the acceleration will continue indefinitely. Galaxies will drift farther and farther apart. Eventually, in hundreds of billions of years, distant galaxies will recede so fast that their light can no longer reach us. The observable universe will shrink. The sky will grow dark as distant lights disappear beyond the cosmic horizon, one by one, until only our local group of galaxies remains, a small island in an expanding ocean of darkness. Even those nearby galaxies will eventually exhaust their gas, stop forming stars, and fade. The last stars will burn out. Black holes will slowly evaporate through Hawking radiation over timescales so vast they make the current age of the universe seem like an eye blink. Eventually, in 100 years or more, even black holes will be gone, leaving nothing but an increasingly cold, dark, empty space expanding forever. Some call this the heat death or the big freeze. Not an ending with drama, but a gradual fading into stillness and silence and cold. The universe doesn't end with a bang, but with an infinite whimper, growing emptier and darker and colder without bound. But this assumes dark energy remains constant. If it changes, strengthens or weakens, the fate could be different. If it strengthens enough, the expansion could accelerate so much that eventually even atoms tear apart, a scenario called the Big Rip. If it weakens or reverses, gravity might eventually pull everything back together into a big crunch, possibly leading to another Big Bang and a cyclic universe. We don't know which future awaits. We're passengers on a ship sailing into darkness, unsure if the journey has an end or just continues into deeper and deeper night forever. Quantum tunneling is one of those phenomena that's confirmed by countless experiments, used in technologies from transistors to electron microscopes, and yet remains profoundly strange when you think about it. It allows particles to pass through barriers they don't have enough energy to overcome, like a ball rolling through a hill instead of over it. Imagine rolling a ball toward a hill. If it doesn't have enough speed, it stops and rolls back. It can't go through the hill because it lacks the energy to get over the top. In the classical world, that's always what happens. But in the quantum world, there's a probability, small but real, that the particle will appear on the other side of the barrier, as if it tunneled through. It's not that it found a path through, or that it borrowed energy temporarily. The particle literally doesn't have enough energy, and yet it sometimes ends up on the other side anyway. Probability waves extend into the barrier, and on the far side, there's a small amplitude for the particle to materialize there. It violates intuition completely, and yet, without quantum tunneling, the sun wouldn't shine. The protons in the sun's core don't actually have enough energy to overcome their electrical repulsion and fuse together. They tunnel through the repulsive barrier, allowing fusion to occur at temperatures far lower than would otherwise be needed. Every photon of sunlight, every plant that grew, every breath you've taken traces back to particles tunneling through barriers they had no business crossing. It's been demonstrated in laboratory after laboratory, with electrons, atoms, even molecules. It's real. But why? Why does reality permit this? The equations predict it, but the meaning, the reason why the universe allows particles to occasionally ignore energy barriers, remains mysterious. It's like discovering that baseballs sometimes pass through walls if you throw them enough times, and being told that's just how probability works at small scales, which is true but doesn't quite dispel the sense that reality is stranger than it should be. The Pauli exclusion principle states that no two identical fermions, particles like electrons, protons, or neutrons, can occupy the same quantum state simultaneously. It sounds technical, but it's why matter has solidity, why you don't fall through your chair, why atoms have structure instead of collapsing into points. Without the exclusion principle, all the electrons in an atom could drop into the lowest energy level. All atoms would be tiny, dense, and chemically identical. There would be no chemistry, no complexity, no variety. The universe would be unrecognizable, a sea of identical, compressed matter with no interesting structure. But why? Why can't two electrons occupy the same state? The mathematical formalism describes it. Fermion wave functions must be antisymmetric under particle exchange, which leads to the exclusion principle. But that's describing what happens, not explaining why. It's one of the fundamental rules of quantum mechanics, taken as axiomatic, but the reason behind the rule, if there is one, remains hidden. Some physicists see it as a consequence of deeper symmetries, connections between spin and statistics that emerge from the structure of space-time itself. Others view it as simply one of the basic features reality happens to have, a boundary condition on existence. Either way, it's a rule that makes the universe what it is, and we don't know why reality chose to implement it. It's like being told the universe runs on software, and you've found a critical line of code that makes everything work, but you don't know who wrote it or why they made that choice. The exclusion principle is woven into the fabric of matter, preventing collapse, enabling chemistry, making life possible, and we accept it because we must, because everything we observe confirms it, even as we wonder about its ultimate origin. In the 1970s and 1980s, NASA launched the Pioneer 10 and Pioneer 11 spacecraft on missions to explore the outer solar system. They visited Jupiter and Saturn, sent back stunning images, and then continued outward toward interstellar space. They were expected to coast along predictable trajectories, pulled by the sun's gravity in ways we could calculate with extraordinary precision. But something strange happened. Both spacecraft started drifting off course, very slightly but measurably. They were decelerating, slowing down by a tiny amount that shouldn't have been there. The effect was small, about 1/10,000,000th of Earth's gravity, but it was real and consistent. For years, this was a genuine mystery. Scientists called it the Pioneer Anomaly, and it sparked all sorts of speculation. Was there an undiscovered planet? Were the laws of gravity different at vast distances? Was dark matter interacting with the spacecraft? Some even proposed modifications to general relativity, new physics that would only become apparent at the solar system's edge. Eventually, though, a more mundane explanation emerged: thermal radiation. The spacecraft had plutonium power sources that generated heat, and that heat radiated unevenly, creating a tiny thrust like a gentle rocket push, always in the direction opposite to the spacecraft's motion, causing the deceleration. When researchers carefully modeled all the thermal effects, accounting for every surface, every component, the anomaly disappeared. It was a triumph of careful analysis, but also a reminder of how difficult spaceflight is to understand perfectly. Even after decades of study, it took years to explain a tiny discrepancy. And while the Pioneer anomaly has likely been solved, it shows how mysteries can linger, how even our most precise measurements can hide subtle effects we don't immediately understand. Still, some wonder. The thermal explanation works for most of the anomaly, but does it account for all of it? Are there still tiny residual effects that hint at something deeper? Probably not, but space is vast and strange. And it's hard to be completely certain about anything happening billions of miles from home. Are we living in the only universe? Or is our cosmos just one among countless others, each with different properties, different laws, different possibilities? This is the multiverse concept, and it emerges naturally from several independent areas of physics: inflation, string theory, quantum mechanics, even though we may never be able to prove it. If inflation happened, that exponential expansion in the first fraction of a second after the Big Bang, it probably didn't happen just once in just one place. Quantum fluctuations would have caused different regions to stop inflating at different times, creating separate bubble universes, each one an entire cosmos unto itself. Those bubbles would still be forming endlessly in an eternally inflating megaverse. Each bubble might have different properties, different constants of nature, different numbers of dimensions, different particles and forces. Most would be sterile, lifeless, unable to support complexity. But in the infinite set of possibilities, some would have the right conditions for stars, planets, chemistry, life. We'd necessarily find ourselves in one of those because we couldn't exist anywhere else. String theory suggests something similar through what's called the landscape problem. The theory has a vast number of possible solutions, maybe 10,500 or more, each corresponding to a different vacuum state with different physics. If all those solutions are realized somewhere, that's a multiverse of staggering diversity. And then there's the many worlds interpretation of quantum mechanics, which says that every time a quantum measurement occurs, reality splits into branches, one for each possible outcome. Every time an electron could go left or right, both happen in different worlds. The number of worlds multiplies incomprehensibly with every quantum event everywhere in the universe, creating an ever-branching tree of parallel realities. But here's the problem. If other universes exist, they're probably fundamentally undetectable. We can't travel to them, can't see them, can't measure them directly. They're beyond our cosmic horizon, separated from us by regions of space expanding faster than light, or by barriers in extra dimensions, or by the branching of quantum possibilities. The multiverse might be real and yet forever beyond proof. Some scientists find this concept useful, even beautiful. It explains why our universe seems fine-tuned without requiring design. Others reject it as unfalsifiable, not even wrong because it can't be tested. And some simply accept the uncertainty, acknowledging that reality might be vastly larger than what we can observe, and we may never know for certain. It's a strange place to be, contemplating infinite other worlds while lying in bed in this one, the only one we can ever touch. Why does time flow forward? Why do we remember the past but not the future? Why do eggs break but never spontaneously reassemble? These questions all point to something called the arrow of time, the directedness of temporal experience, the fact that time seems to have a one-way flow. The usual explanation involves entropy, a measure of disorder or randomness in a system. The second law of thermodynamics says that entropy tends to increase in closed systems. Things become more disordered over time. A broken egg is more disordered than an intact one. Smoke disperses rather than gathering. Heat flows from hot to cold, and never the reverse. And this gives us an arrow, a direction. We can tell time is moving forward because entropy is increasing. Disorder is growing. Things are breaking down and spreading out. The past is the direction of lower entropy. The future is the direction of higher entropy. But this just pushes the mystery back one step. Why did the universe start with such low entropy? The Big Bang was an incredibly ordered state. All the energy concentrated, everything smooth and uniform. If it had started in a high entropy state, there would have been no arrow of time, no direction for things to flow, no way for complexity to emerge. Some cosmologists propose that our low entropy beginning is just a statistical fluctuation in an eternal, high entropy universe, a random dip that created a pocket of order, like a wave rising in a calm sea. Others think it might be related to gravity, which becomes more ordered as it clumps matter together rather than spreading it out, opposite to most other forces. Still, others invoke the multiverse, suggesting that different universes have different entropy histories, and we find ourselves in one where an arrow exists because only such universes can support observers. Whatever the reason, the arrow of time is intimately connected to our existence. Consciousness requires memory, which requires the ability to distinguish past from future, which requires increasing entropy. We are creatures of the arrow, shaped by it, unable to exist without it. And yet we don't know why it points the way it does, why time flows from this direction we call past toward this direction we call future, carrying us along like leaves on a river we can't see. Here's one of the deepest problems in theoretical physics. Quantum mechanics and general relativity are both spectacularly successful theories, each verified to extraordinary precision in its domain, and yet they're fundamentally incompatible with each other. They can't both be completely correct, or at least they can't both be describing reality in the ways we think they are. Quantum mechanics describes the behavior of particles and forces at small scales using probabilities, uncertainties, and discrete quantum states. Reality at the quantum level is fuzzy, indeterminate, described by wave functions that evolve smoothly until measurement collapses them. General relativity describes gravity and the structure of space-time at large scales using smooth, curved geometry. Mass and energy bend space-time, and that curvature is what we experience as gravity. It's deterministic, continuous, elegant in its mathematical structure. But when you try to combine them, when you need both quantum mechanics and gravity, as you would near a black hole's center, or during the first moments of the Big Bang, the theories contradict each other. The math produces infinities and nonsense. General relativity treats space-time as a smooth fabric, but quantum mechanics suggests everything should fluctuate at small scales. You can't have both a perfectly smooth geometry and quantum uncertainty in the same description. Physicists have been trying to reconcile these theories for nearly a century. String theory, loop quantum gravity, and other approaches each offer possible solutions, but none have been confirmed experimentally. We don't have a theory of quantum gravity, a framework that successfully merges the quantum and gravitational worlds. And until we do, there are questions we simply can't answer. What happens at the center of a black hole, where both quantum effects and gravity are strong? What happened at the moment of the Big Bang? How does space-time itself behave at the smallest scales? These questions require quantum gravity, and quantum gravity remains one of the great unsolved problems in physics. It's as if we have two different maps of reality, each accurate in its own territory. But when we try to overlap them where the territories meet, They don't align. And we're left wondering which map is wrong, or if we need an entirely different kind of map we haven't imagined yet. Let's return once more to dark energy, but from a different angle, what physicists call the cosmological constant problem. Einstein originally introduced the cosmological constant in his equations as a fudge factor to keep the universe static, which was what everyone believed at the time. When Hubble discovered the universe was expanding, Einstein supposedly called it his greatest blunder and removed the constant. But it came back. Modern observations suggest the universe does have a cosmological constant, a tiny energy density in empty space that causes accelerating expansion. It's small, but not zero, and that's the problem. When quantum field theory calculates what the cosmological constant should be, considering the vacuum energy from all quantum fields, the answer is huge, roughly 10^120 times larger than what we observe. Some contributions to the calculation can be negative, and some positive, so in principle they could cancel. But to get the observed value, you'd need cancellation accurate to 120 decimal places. All those positive and negative contributions would have to balance almost perfectly, leaving only a tiny remainder. That level of fine-tuning seems absurd. It's like dropping a pencil and having it land balanced on its point, then discovering it's been balanced not just approximately, but to within the width of an atom. Possible, perhaps, but so improbable that you'd suspect something else is going on. Some invoke the anthropic principle. If the cosmological constant were much larger, the universe would have expanded so fast that galaxies couldn't form, stars wouldn't exist, and no observers would be around to measure anything. In a multiverse with varying constants, we necessarily find ourselves in one of the rare universes where the value permits our existence. Others think there must be a symmetry or mechanism we haven't discovered that naturally drives the cosmological constant toward zero, and the small observed value is a deviation from exact zero for reasons we don't yet understand. Still others wonder if we're calculating the vacuum energy wrong, if quantum field theory breaks down in some way at cosmic scales, or if our whole framework for thinking about empty space needs revision. Whatever the answer, it's embarrassing for physics that our best calculation is off by 120 orders of magnitude. It suggests we're missing something fundamental about how space, energy, and quantum mechanics fit together. Something so basic that once we see it, the whole problem might dissolve. Or it might point to a multiverse, to fine-tuning, to anthropic reasoning that makes physicists uncomfortable because it feels like giving up on deeper explanation. The cosmological constant problem remains open, a chasm between prediction and observation that swallows conventional understanding. At the center of a black hole, general relativity predicts a singularity, a point of infinite density where the curvature of space-time becomes infinite, where all the mass that fell in is crushed down to zero volume. It's where the mathematics breaks down completely, producing infinities that signal the theory's failure. Do singularities actually exist? Or are they artifacts of pushing general relativity beyond its valid domain? Most physicists suspect the latter, that quantum effects become important at very small scales, and a proper theory of quantum gravity would resolve the singularity into something else, something finite, though perhaps very strange. But we don't have that theory, so we can't say for certain what lies at a black hole's center. It might be a region where space-time itself becomes quantized, grainy rather than smooth. It might be a place where the concepts of space and time cease to have meaning. Some speculations involve wormholes, connections to other regions of space-time or other universes entirely, though there's no evidence for this. The singularity is hidden behind the event horizon, the boundary beyond which nothing can escape. That's a kind of cosmic censorship. Whatever strange things happen at the singularity, they're veiled from outside observers. We can't see in, can't send probes to report back, can't test our theories against what's actually there. Even if you fell into a black hole yourself, you wouldn't experience the singularity the way general relativity describes it. Tidal forces would stretch and compress you long before you reach the center, a process gruesomely called spaghettification. And from your perspective, you'd cross the event horizon in finite time and reach the singularity shortly after. But the mathematics describing what happens there would be meaningless. Infinities everywhere, physics giving up. So the center of a black hole remains one of the great unknowns. It's a place where our best theory points and says, "Here be dragons," admitting its own inadequacy. And until we have quantum gravity, until we can describe what happens when all the mass of a collapsing star is compressed into regions smaller than atoms, the singularity remains a placeholder in our understanding, a question mark at the heart of darkness. The speed of light, 219 and 792 458 meters per second, is the universe's ultimate speed limit. Nothing can travel faster, not spaceships, not particles, not information. It's woven into the structure of space-time itself, appearing in Einstein's equations as a fundamental constant that relates space and time. But why? Why does the universe have a speed limit at all? And why is it this particular speed rather than something else? Part of the answer is that the speed of light isn't really about light. It's the speed of causality, the maximum rate at which cause and effect can propagate. Light travels at this speed because photons are massless, and massless particles always travel at the maximum speed the universe allows. If we lived in a universe with no light, the speed limit would still exist. It's a property of space-time, not of light specifically. But that just rephrases the question, why does space-time have this speed built into it? The value appears in the relationship between space and time, in the conversion factor that lets us treat time as a kind of dimension similar to space. It shows up in ERMC2, connecting energy and mass. It governs how electric and magnetic fields interact. It's everywhere in physics, a fundamental scale that sets the structure of reality. And yet, from a deeper perspective, it seems arbitrary. There's no equation that derives the speed of light from more fundamental principles. We measure it, find its value, and plug it into our theories. If it were different, faster or slower, the universe would work differently. But we don't know why it has this particular value. Some theories propose that the speed of light might not be constant, that it could have been different in the early universe, or might vary in extreme conditions. These ideas remain speculative, but they highlight how little we understand about why physical constants are what they are. The speed of light is one of the most precisely measured numbers in all of physics, a cornerstone of relativity and quantum field theory, and we don't know why it's the speed it is. We just know that it is, and everything else follows from that. We exist because of an imbalance. In the first moments after the Big Bang, matter and antimatter were created in nearly equal amounts, but not quite equal. For every billion antiprotons, there were 1,000,000,001 protons. For every billion positrons, 1,000,000,001 electrons. A tiny asymmetry, 1 part in a billion. Matter and antimatter annihilate when they meet, converting mass into energy. All those billions of particle-antiparticle pairs destroyed each other, leaving only radiation. But that one extra matter particle per billion, the slight excess, survived. Those survivors became everything. All the atoms in all the stars, all the galaxies, all the planets, everything we see and are. We're the cosmic remainder, the leftover particles that didn't have antimatter partners to annihilate with. But why was there an asymmetry? This is the mystery of baryogenesis, the process that created more matter than antimatter. According to our best theories, the Big Bang should have produced them equally. Creating more matter than antimatter requires violating certain symmetries, and while the Standard Model allows for small violations, they're not nearly enough to explain the observed imbalance. Some theories propose new physics beyond the Standard Model, additional particles or interactions that could have preferentially created matter in the early universe. Others invoke special conditions during inflation, or processes involving grand unified theories, or subtle quantum effects in the Higgs field. Each has problems, and none have been confirmed. There's also the puzzling absence of antimatter today. If matter and antimatter were created in the Big Bang, even with a slight imbalance, you'd expect to find pockets of antimatter somewhere in the universe. Antimatter galaxies, antimatter stars. Astronomers look for signs of matter-antimatter annihilation at boundaries where regions might meet, but so far, nothing. The universe seems to be made entirely of matter, with antimatter only appearing briefly in high-energy processes before quickly annihilating. So we're left with a fundamental mystery about our own existence. That one extra matter particle per billion, that tiny asymmetry that allowed anything to exist at all, we don't know where it came from or why it has the magnitude it does. We're the result of an imbalance we don't understand, survivors of an asymmetry that seems both essential and inexplicable. The Fermi paradox asks a question that sounds simple, but leads to unsettling places. If the universe is so vast and old, containing billions of galaxies with trillions of stars, many with planets that could harbor life, why haven't we detected any signs of alien civilizations? Where is everybody? The numbers seem overwhelming. Our galaxy alone has hundreds of billions of stars. Many have planets in habitable zones where liquid water could exist. Even if intelligent life is rare, say it emerges around only one star in a million, there should still be hundreds of thousands of technological civilizations in the Milky Way. And the universe has been around for nearly 14 billion years, giving civilizations plenty of time to arise, spread, and make their presence known. Yet we see nothing. No radio signals that are obviously artificial. No megastructures around distant stars harvesting energy. No evidence of interstellar travel or terraforming. The sky is silent. The cosmos appears empty of other minds. Why? The possible answers are called solutions to the Fermi paradox, and each is troubling in its own way. Maybe life is incredibly rare, the sequence of events leading from chemistry to intelligence so improbable that it's happened only once in the Observable universe. Maybe intelligent life destroys itself quickly, doomed by its own technology before it can reach the stars. Maybe civilizations hide deliberately, staying quiet to avoid attention from something dangerous. Maybe they're here already, but so advanced we can't recognize their presence, the way ants don't notice satellite transmissions. Or maybe intelligence is common, but space is simply too vast. The distances between stars are so enormous that even civilizations millions of years older than us might not have reached us yet, might not have sent signals that have had time to arrive. Maybe we're just early, among the first intelligent species to emerge in a universe that will eventually be full of life. Each explanation suggests something about our place in the cosmos. If we're alone, we're precious and lonely. If others exist but we can't find them, we're isolated by distance or time or our own limitations. If civilizations tend to destroy themselves, we're facing the same fate. The silence of the universe is a mystery, yes, but also a mirror, reflecting our fears and hopes about what it means to be conscious beings in an ancient, enormous cosmos. Imagine traveling in a straight line through the universe, going farther and farther for billions and trillions of light years. Would you eventually return to where you started, like Magellan sailing around Earth? Or would you continue forever into infinite space? This is the question of the universe's topology, its large-scale shape. Measurements suggest the universe is spatially flat, which could mean it's infinite, extending forever in all directions. But flat doesn't necessarily mean infinite. You could have a flat universe that loops back on itself, like the surface of a torus, a donut shape, where traveling far enough in one direction eventually brings you back to your starting point. If the universe loops, it could be finite in extent, even though it has no edge or boundary. There would be no place you could point to as the universe's end, no wall you'd run into. But if you traveled far enough, you'd eventually see the back of your own head, or at least the light that left from where you were billions of years ago. Some cosmologists have looked for signs of this by searching for repeating patterns in the cosmic microwave background, matching circles or structures that might indicate we're seeing the same regions of space from different directions. So far, no clear evidence has been found, which suggests that if the universe does loop, it's larger than the observable universe, meaning we couldn't detect the repetition, even if it exists. So we don't know if the universe is finite or infinite. Both seem possible. An infinite universe is conceptually challenging. Infinite stars, infinite galaxies, infinite copies of you somewhere doing slightly different things. If the universe is both infinite and uniform, a finite looping universe is geometrically strange. There's no center, no edge, but there's a size. It's another basic question about reality that remains unanswered. The stage on which everything plays out might extend forever, or it might wrap around on itself in dimensions we can't directly perceive. And lying here in the darkness, you can contemplate both possibilities. That existence might be endless, or might curve back in ways that make endless and finite less different than they seem. Lithium is the third element in the periodic table, right after hydrogen and helium. It's light, reactive, used in batteries found in our smartphones and electric cars. It's also at the center of a cosmological mystery called the lithium problem. Big Bang nucleosynthesis, the production of light elements in the first few minutes after the Big Bang, is one of the great successes of modern cosmology. We can calculate how much hydrogen, helium, deuterium, and lithium should have been created, and our predictions match observations remarkably well. Mostly. The problem is lithium-7. When we look at the oldest stars in the universe, stars that formed from gas close to the Big Bang's primordial composition, we find about 3 times less lithium than our calculations predict. It's a significant discrepancy, not just a minor measurement issue. Why? Several possibilities exist, none fully satisfactory. Maybe something destroyed lithium in the early universe, some process or particle we don't know about that preferentially broke down lithium atoms. Maybe stars have destroyed more lithium than we thought, mixing it into their hot interiors where it's burned away. Maybe our measurements of primordial abundances are harder than we think, and the old stars we're observing aren't quite as pristine as we assume. Or maybe, and this is the more intriguing possibility, there's new physics at work. The lithium problem might be telling us that something happened in the early universe that we don't understand. Some deviation from the standard model or from standard cosmology. Perhaps there were additional relativistic particles present during nucleosynthesis, or maybe the fundamental constants were slightly different, or maybe exotic physics altered reaction rates. It's a small discrepancy compared to some cosmic mysteries, but it's persistent and puzzling. Our model of the early universe works so well for other elements that the lithium problem stands out like a wrong note in an otherwise perfect symphony. Something happened to lithium, or something about our understanding is incomplete, and we're still trying to figure out which. Protons are everywhere, in your body, in every atom of ordinary matter, in every star and planet and grain of dust. They're stable, as far as we can tell, lasting essentially forever. But do they truly last forever? Or do protons eventually decay, given enough time? Some theories that try to unify the fundamental forces, grand unified theories, predict that protons should be unstable. They shouldn't last forever, but should eventually decay into lighter particles, like positrons and photons. The predicted lifetime is enormous, something like 1034 years or longer, a trillion times the current age of the universe. But it's not infinite. To test this, physicists have built experiments. Enormous tanks of ultra-pure water or other materials surrounded by detectors, sitting in deep underground mines to shield from cosmic rays. They watch and wait for a single proton to decay. If you have enough protons, and a tank of water has something like 10^33 of them, you might see one decay even if the average lifetime is absurdly long. Decades of observation have seen nothing. No clear proton decays. This rules out the simpler grand unified theories and pushes the minimum possible lifetime longer and longer. But it doesn't prove protons are stable forever, just that if they decay, they do so more slowly than we've been able to measure. This matters because if protons do decay, eventually everything made of matter will disintegrate. In the unimaginably distant future, long after the last stars have burned out and black holes have evaporated, even the atoms themselves would fall apart, dissolving into radiation. The universe would contain no stable matter at all, just photons, and perhaps exotic particles, in an increasingly cold and empty expanse. But if protons are truly stable, if they last literally forever, then at least some structures persist, even in the deep cosmic future. Frozen iron spheres drifting through darkness, remnants of dead worlds, would endure indefinitely, monuments to the fact that matter once organized itself into complexity. We don't know which future awaits. The stability of protons, something we take completely for granted, is still an open question. Reality might be built on structures that last forever, or everything might be temporary, even matter itself, given enough time. Here's a quantum oddity called the quantum Zeno effect. If you continuously observe a quantum system, you can prevent it from changing. Measurement itself freezes evolution, like a watched pot that never boils, except this is real and has been demonstrated in laboratories. Normally, quantum systems evolve smoothly according to Schrödinger's equation. An excited atom will decay to a lower energy state, emitting a photon. A radioactive nucleus will eventually decay. A particle in one state will transition to another. These processes take time, and they're probabilistic. You can't predict exactly when they'll happen, only the probability per unit time. But if you measure the system repeatedly, checking whether it has decayed yet, the repeated measurements actually suppress the decay. The more frequently you check, the more you inhibit the transition. Check continuously, and the system never evolves at all. It's frozen in its initial state by the act of observation. It's named after Zeno's paradox, the ancient argument that motion is impossible because before you can travel any distance, you must first travel half that distance, and before that, half of the half, and so on infinitely. Similarly, before a quantum transition can complete, it must first get halfway there, but measurement collapses it back to the start, and you can repeat this indefinitely, preventing completion. The quantum Zeno effect has practical applications in quantum computing and quantum information, where you might want to protect quantum states from decoherence. But it's also deeply strange, philosophically. It suggests that the act of observation isn't passive, that looking at something affects its evolution in fundamental ways, not just by disturbing it mechanically, but by interrupting its quantum possibilities. It's as if reality only moves forward when no one's watching, and continuous observation literally freezes time for the observed system, which raises questions about what observation means, what qualifies as a measurement, and whether the universe's evolution depends on when and how it's observed. These questions remain open, part of the broader mystery of quantum measurement, the boundary between possibility and actuality. Saturn has a hexagon at its north pole. It's not a small feature. The hexagon is wider than Earth, a six-sided jet stream in the planet's atmosphere that maintains its shape with remarkable stability. It was first photographed by the Voyager spacecraft in the 1980s, and when the Cassini probe arrived decades later, it was still there, unchanged, spinning at the pole like a cosmic mandala. Why a hexagon? Why not a circle, or an oval, or some irregular, turbulent pattern? Atmospheric dynamics don't typically produce geometric shapes, especially not shapes that persist for decades or longer. Scientists can reproduce hexagons in laboratory experiments with rotating fluids. Spin a cylindrical tank at the right speeds with the right fluid viscosity, and hexagonal patterns emerge. Something about the fluid dynamics, the rotation rates, the interactions between different flow speeds creates stable polygonal structures, so the phenomenon isn't completely mysterious. We understand that it can happen, But the stability and size of Saturn's hexagon remain puzzling. Most atmospheric patterns are transient. They form, evolve, dissipate. Weather on Earth changes constantly. Even Jupiter's great red spot, though long-lived, varies in size and intensity. Saturn's hexagon, by contrast, seems remarkably persistent, maintaining its shape year after year despite the turbulent dynamics of the atmosphere around it. Recent observations show there's a corresponding vortex at the center of the hexagon, spinning rapidly at the pole itself. The interaction between this vortex and the surrounding winds might help stabilize the hexagonal pattern. But the full picture, why this particular geometry, why it's so stable, what keeps it from distorting or breaking up, isn't completely understood. It's a reminder that even in our own solar system, places we've visited with spacecraft and studied for decades, mysteries remain. A hexagon wider than Earth, spinning at Saturn's pole for longer than human civilization has existed, maintained by atmospheric processes we only partially understand. Nature produces patterns that look artificial, shapes that seem designed, emerging from nothing more than gas and motion and the laws of physics. Something enormous is pulling our galaxy through space. We call it the Great Attractor, a gravitational anomaly located roughly 200 million light-years away, pulling the Milky Way and thousands of other galaxies toward it at speeds of several hundred kilometers per second. We know it's there from its gravitational effects, but we can't see what it is. The problem is that the Great Attractor lies in a region astronomers call the zone of avoidance, a swath of sky obscured by the disk of our own Milky Way. Stars, dust, and gas in our galaxy block our view, making it nearly impossible to observe whatever lies beyond in that direction. It's like trying to see something on the other side of a thick forest. You know there's something there from its effects, but you can't get a direct look. Recent observations using wavelengths that penetrate the obscuration have revealed that the region contains massive galaxy clusters and superclusters, huge concentrations of matter that could account for the gravitational pull. In fact, there's an even larger structure called the Shapley supercluster beyond the Great Attractor, and some of the motion might be toward that instead. But the full picture remains unclear. How much of the motion is due to the Great Attractor itself, and how much to more distant structures? Is there something even larger and more massive beyond what we can currently see? Are there voids pushing from behind, or is it all attraction from ahead? We're passengers on a galactic ship being pulled towards something we can barely discern through cosmic fog. The journey will take hundreds of millions of years and will never arrive. Our sun will burn out long before the Milky Way reaches whatever is pulling us. But the fact that we're moving at all, that something massive enough to drag galaxies, is hidden just beyond our ability to see clearly, is a reminder of how much remains unknown, even about the local cosmic geography. Are the laws of physics the same everywhere? It's a foundational assumption of science that an electron behaves the same way here as in a distant galaxy, that the speed of light is constant everywhere, that the fundamental constants don't vary across space and time. But is this actually true? Some observations have hinted, tentatively, controversially, that the fine structure constant, a number that characterizes the strength of the electromagnetic interactions, might be very slightly different in galaxies billions of light years away. the differences are tiny, maybe 1 part in 100,000, and the results are disputed. Other studies find no variation, but the mere possibility is unsettling. If fundamental constants vary across the universe, it would transform our understanding of reality. The laws of physics wouldn't be universal laws, but local bylaws, rules that happen to apply in our cosmic neighborhood, but differ elsewhere. Chemistry would work differently in distant regions. Stars might burn differently. Life might require different conditions. It could also mean the constants change with time, that the early universe had different physics than today, and the far future might differ from now. This would complicate how we interpret observations of distant objects, since we're seeing them as they were billions of years ago when the light left them. Most physicists expect the constants to be truly constant, that the apparent variations, if real, will turn out to be measurement errors or misinterpretations. The mathematical structure of physics seems to hang together in ways that would break if constants varied too much. But we can only test this by making observations, looking at atomic spectra in distant quasars, analyzing the cosmic microwave background, searching for any signs of variation. We might live in a universe where the laws are the same everywhere and always, where physics discovered on Earth applies unchanged across all of space and time. Or we might live in something more like a patchwork, where different regions have subtly different rules. For now, we don't know for certain, though the evidence leans toward uniformity. It's another basic assumption that mostly seems right, but remains open to question. And so we arrive at the final mystery, perhaps the largest of all. How does the universe end? What is the ultimate fate of everything? The stars, the galaxies, space itself. Current evidence suggests we're headed toward what's called the heat death, or the big freeze. Dark energy will continue accelerating the expansion forever. Galaxies will drift beyond each other's horizons, disappearing into cosmic darkness. Star formation will cease as galaxies exhaust their gas. The last stars will burn out in 100 trillion years or so. White dwarfs will cool to black dwarfs. Neutron stars will grow cold. Black holes will slowly evaporate through Hawking radiation over timescales of 10-100 years or longer. Eventually, in an almost incomprehensibly distant future, nothing will remain but photons, neutrinos, and perhaps exotic particles spreading ever thinner through an ever larger space. Temperature will approach absolute zero asymptotically, never quite reaching it, but getting arbitrarily close. Entropy will approach maximum, perfect disorder, perfect equilibrium, nothing happening anywhere because there's no energy gradient to drive change. It's an ending without drama, not a bang, but an infinite whimper, a fading into silence and stillness and cold that never ends because there's no one left to notice it ending. But this assumes dark energy remains constant. If it strengthens, the expansion could accelerate so much that eventually even atoms tear apart. The Big Rip, where everything is pulled to pieces by expanding space itself. If dark energy weakens or reverses, gravity might eventually win, pulling everything back together in a big crunch, possibly followed by another Big Bang, a cyclical universe dying and rebirthing eternally. Or perhaps quantum effects allow tunneling to a different vacuum state, and the universe suddenly reconfigures itself with different physics, different particles, different rules, a transition so complete that nothing survives it. Or perhaps consciousness or intelligence plays a role in ways we can't foresee, manipulating physics in the far future to prevent the heat death, to extract energy from black holes, to persist somehow in ways that seem impossible now. We don't know. The universe's fate depends on the nature of dark energy, on whether protons decay, on quantum gravity effects we can't calculate, on whether the laws of physics themselves might change. We're living in the early stages of cosmic history, the first few % of the universe's lifetime, if current models are right. And we're trying to predict how the whole story ends based on the opening chapters. What we do know is that everything changes. The stars that seem eternal will burn out. The galaxies that appear permanent will disperse or darken. Even black holes evaporate eventually. Nothing lasts forever in its current form. The universe is a temporary arrangement, patterns emerging briefly from the underlying quantum fields before dissolving back into simplicity and silence. And yet, here we are, in this moment. The universe keeps its secrets even as it reveals itself. And maybe that balance between knowing and not knowing, between understanding and mystery, is where wonder lives, where curiosity can flourish without anxiety, where we can contemplate the largest questions existence offers and then let them go, returning to the gentle darkness of sleep, the personal mystery of consciousness fading into dreams. And so we've journeyed through 50 mysteries, questions without answers, riddles without solutions, places where science reaches its current boundaries and admits uncertainty, dark matter and dark energy filling the cosmos with invisibility, the arrow of time pointing forward for reasons we don't fully understand, quantum particles existing in superposition until observed, entangled across cosmic distances, tunneling through barriers they shouldn't cross. The universe's fine-tuned constants, its flat geometry, its mysterious uniformity, fast radio bursts and ball lightning, cosmic rays with impossible energies, signals from space that never repeat, consciousness emerging from neurons, mass arising from fields, the multiverse question that might be fundamentally unanswerable. And finally, the ending, whatever form it takes, heat death or big rip or something we haven't imagined. These aren't failures of science, but honest acknowledgments of what we don't yet know, what we may never know. They're invitations to wonder, to contemplation, to accepting that reality is richer and stranger than any theory we've yet created. And perhaps there's something restful in that, in knowing that not everything is solved, not everything is explained, that the universe retains its capacity to surprise us, to humble us, to remind us that we're part of something vast and ancient and ongoing. So let these mysteries settle around you like a comfortable blanket. You don't need to solve them. You don't need to hold on to them. They'll still be there tomorrow and the day after, waiting patiently for new observations, new theories, new minds to wrestle with them. For now, just rest. Let your breathing slow. Let your thoughts drift like galaxies separating in the expanding cosmos. You're a small pattern of matter and energy, briefly organized into consciousness, briefly aware of the larger patterns, briefly capable of wonder. And that's enough. That's everything. Thank you for exploring these mysteries with me tonight. Until next time, sleep well and let the universe keep its secrets while you rest in yours. Good night.